Hello, health science students. This is Professor Van Dyke with your week 13 video. Tonight we're going to be talking about water quality. So we have 31 slides. It's pretty straightforward material. When we talk about food quality, you'll notice that there are a lot of common themes in regard to water quality and food quality. So let's go ahead and jump right in with the week 13 video. So with water quality, what we're going to talk about is waterborne diseases, water pollution, some legislative components, pollution sources. So we'll talk about non-point sources and point sources, which are very easy to tell apart, and we'll talk about that when we get to it. Let's move on to slide 2. So in the past, water quality was exceedingly challenging to try to provide for growing societies, and it certainly became an issue as people began to urbanize and move into cities. So it used to be that the most dangerous thing you could do was drink water. So everybody probably remembers with the Broad Street pump. This was kind of an early foray into epidemiology, and essentially what they found, specifically John Snow found that there was a pump handle that was providing water to individuals. The water was tainted and making people very sick. So they removed the pump handle at the Broad Street well, and lo and behold, people got better. Now, one of the funny things is that there was a group of individuals that were working right across the street from the Broad Street pump that were not getting sick from waterborne diseases from the specific water source. And I'm sure you all know who they were. They were the people that worked at the factory that essentially was making beer. So they were drinking their beer, they weren't drinking the water across the street, and they stayed healthy. So as I mentioned before, water has traditionally in the past been a very dangerous thing to drink for a number of reasons. One being that we allow our animals to wade into the water and drink, and they put their own fecal contamination into it. But also, in addition, we do the same thing. We very readily contaminate our water sources with all kinds of dangerous things like fecal contamination, sludge that is laden with chemicals, things like that. So some of those waterborne illnesses can be cholera, typhoid, paratyphoid, things like that. So very recently we've noticed that water quality is definitely something that has increased substantially because we have so many water districts and things like that. They do a wonderful job of providing us with our drinking water. A lot of that certainly can be traced to specific individuals that were groundbreaking in the fact that they wanted to try to put something as dangerous as chlorine into the water, but certainly that was a huge leap forward in regard to water quality. On to slide 3. So symptoms are going to be pretty much the same for all of the different waterborne diseases. So they can be divided into 3 groups. So we have bacterial, viral, and protozoal. They're all going to essentially cause the same thing. They're going to cause prostration, a very cramped stomach, diarrhea, nausea, vomiting, and fever as well. So very painful. If you've ever gotten a waterborne disease, it is exceedingly painful, and certainly the protozoals tend to stick around for quite some time. It can be very painful to treat as well. On to slide 4. So we're going to divide these up, as I had mentioned, into 3 categories: bacterial, viral, and protozoal. This is the bacterial component. So cholera is caused by Vibrio cholerae, which is a bacteria. Typhoid is caused by Salmonella typhi and 107 other types of Salmonella. Then we have paratyphoid, which is caused by Salmonella enteritis, paratyphi, 3 serotypes of that. All 3 of them are going to cause the same thing, that diarrhea and cramping and things like that. We also have shigellosis, which is caused by Shigella dysenteriae, and then campylobacteriosis caused by Campylobacter enteritis. So again, these are obviously, I'm not going to make you remember all of these, but there may be some questions in regard to being able to tell which one's bacterial, which one is viral, and which one is protozoal. So those will be pretty straightforward for you. But also in regard to bacteria, we also have E. coli, E. coli fever, which is caused by Escherichia coli, E. coli, of course. So everybody's familiar with that, and that is bacterial as well in nature. Onto viral diseases. They're caused by the following viruses. So Hep A virus, Norwalk virus, rotavirus, poliomyelitis, which is the only one that doesn't specifically have the word virus in it. But these are viral diseases that you can get from water. And hepatitis A will affect the liver. It's usually going to be caused by things like sewage systems backing up, heavy rains, things like that. Then you have the Norwalk virus, which is gastrointestinal, rotavirus, which heavily affects children, and then poliomyelitis, which is neuromuscular. Very, very challenging process. If you get poliomyelitis, fortunately, this is a disease that's all been wiped out. But again, certainly something that we have to always watch out for. Slide 6, on to protozoal diseases. So amoebic dysentery caused by Entamoeba histolytica, and then giardiasis, which is caused by Giardia lamblia, and then cryptosporidiosis or traveler's diarrhea, which is caused by Cryptosporidium parvum. So again, these are all protozoal in nature, and the treatment for these is really challenging because to try to kill protozoa in the blood it's tough on an individual. Sometimes it can take several weeks for the treatment. And again, something that is really challenging, but certainly when we look at water quality, we do the very best we can to avoid any interactions with these. The place you're going to run into things like Giardia lamblia, Cryptosporidium parvum. This would be very common if you went to Yosemite and you saw the water and you said, oh, it looks so nice, I want to drink some of this water, and then you drink it and it makes you sick. You could also get this certainly in other places as well. So very challenging to try to deal with protozoal diseases because there's so much fresh water and people just assume that they can drink it, and unfortunately they can't. So moving on to water pollution sources. So again, I'd mentioned there are two types of sources. There are point sources and non-point sources, and we'll go into these in a little bit more detail. A point source for water pollution is where pollutants enter the waterway at well-defined points, like pipes and ditches and sewage outfalls. Now, non-point sources are a little bit more hard to define. They're going to be caused by runoff and seepage from broad areas of land. So you can have a whole shelf of land that is draining into an area, and this can be carrying with it animal waste. It can be carrying with it pesticides, particulate matter, all kinds of stuff. So the way that you really can easily define the difference between a point source and a non-point source, can you walk up to it and point at it? That's a point source. There it is, right there. It's a pipe, or it's a ditch, or it's a sewer. So it's very easy to find it. In the picture you see in the middle of this slide, that is essentially a pipe coming out, and that would be a point source of pollution. So on to slide 8, a continuation of non-point sources. So we have agricultural sources. So again, you can't really say, oh, it was one farmer that did this. It could be caused by 20, 30 farms in some areas where pesticides and fertilizers and other chemicals, including sediment like loose soil, is washed away and ends up getting into a waterway or some area that provides drinking water or usable water, potable water for individuals. And then we also have construction activities. These can be caused by paint and cement and asphalt and sedimentation, again, from multiple construction sites. It may just be one, it may be several. And then you also have urban street runoff, household pesticides that we use in our yards, fertilizers that, again, we use in our yards, chemicals that we may use, like things that we use to wash our cars, things we may use as cleaning materials, and then sediment as well. And then fourth is drainage from old acid mines. Water runs into them and then washes out into the hydrologic cycle. And then we also have airborne pollutants that are caused by acid rain. So you remember acid rain from our last lecture, where you have sulfuric acid being formed by SOx combining with water, and that's going to create sulfuric acid, H2SO4, and you also have nitric acid, which is going to be caused by nitrogen, HNO3. This is going to be water combining with nitrogen as well, and that's going to cause acid rain. So these are non-point sources of pollution. You really can't point to them. You can point to the sky and say, oh, it's raining acid rain, but it's coming from all kinds of different places. It's not a point source that you can point to it. So on to slide 9. In 1990, the EPA made a report that said non-point sources of pollution that are running into lakes and streams accounted for about almost 100% of the sedimentation, 98% of bacteria, phosphorus, nitrogen, and biochemical oxygen demand. And we'll talk a little bit about that as we get further into this lecture. Slide 10, how do you prevent non-point sources of pollution? So this can be very challenging because, as you see, there are a lot of different things that you can do, but they're hard to get people to get on board with these things. So one, keep litter and debris out of the gutters and drains. We are really bad at this. I can't tell you how disheartening it is to see people throwing trash out of their car windows and things like that, because it all ends up going into the hydrologic cycle. Eventually that water has to go somewhere carrying that trash with it. There isn't somebody whose job is just to sit there and scoop trash out of our gutters. Number 2, use landscaping chemicals sensibly according to the label, and store them and dispose of them in an appropriate manner. And that's the hard part, is people don't like to go to household hazardous waste to get rid of these things. So they store it for so long, they use a little bit of it, and then they may just dump it into their yards or dump it into the drain. Or they may over-fertilize their yards just to get rid of it, and then it's going to wash out into the drainage system and potentially into a waterway. Number 3, dispose of motor oil and brake fluid and antifreeze properly. This was a very big deal because people didn't know what to do with their motor oil, so they would just dump it down a drain. They're very, very dangerous and very bad for the environment. I actually knew an individual who used to dump it in his backyard, his motor oil, because, and as I quote, it's just dinosaur blood, right? No, it's not. It's heavily processed, and it needs to go to the appropriate place to be recycled. And now this is one of the reasons that, as I'd mentioned, if you don't make it easy for people, they won't do it. So this is why every gas station will collect motor oil, used motor oil, and other things. You can bring them all kinds of mixtures of fluids from your car, and they will take them and recycle all of them. Number 4, manage animal waste to reduce water contamination. So if you have a dog, you definitely want to pick up after your dog, because as the water washes past the fecal matter, it ends up getting into waterways. So definitely manage animal waste. And finally, control the soil erosion with vegetation cover. So if you drive along the freeways, you'll notice that they do this very regularly. They'll use that ground cover that's called crabapple. They may use the one with the purple flowers. They may plant oleanders. Or now they actually will put in rock with cement around it to make a long cement area. And that's going to keep the soil from eroding along those roadways. On to slide 11, water quality legislation. So I don't generally tend to throw any dates on your tests, but this is just to kind of give you an idea for when this stuff was occurring. So the Water Pollution Control Act of 1972 was later amended to the Clean Water Act of 1977. And the important thing about the Clean Water Act is it's not specifically looking at drinking water, okay? That's an important takeaway from this. The Clean Water Act had really nothing to do with drinking water. The goal was to take the nation's waterways and make them fishable and swimmable. So this was kind of a first step into that process upon which we're going to start cleaning up our waterways. And still to this day, we do a very poor job of this. Okay, so from 1972 to the Clean Water Act of 77, we began to start to make those changes. So slide 12 is some kind of interesting terms that I really do kind of want you to understand these terms. I'm pretty sure there's some test questions on this. So with slide 12, when we talk about dissolved oxygen, this is the amount of oxygen that's dissolved in water itself. So moving water, if it's moving rapidly, it has more dissolved oxygen, where stagnant water is going to have much less. So dissolved oxygen is very important. So you may wonder how fish can breathe, essentially how they respire. How are they living in water? It's because of this dissolved oxygen. They're able to strip the dissolved oxygen out of the water and utilize it for respiration. So if the water is just sitting still, it may begin to get like moss over the top of it. This is a process called eutrophication, and that moss is going to utilize that same dissolved oxygen. It's going to be pulling the dissolved oxygen out of the water, which leaves less for the fish and other aquatic organisms. So with BOD, biochemical oxygen demand is a good way to test to see how much dissolved oxygen is needed in that water to actually break down aerobic biological organism materials in any given water sample. So what you're going to have is biochemical oxygen demand is going to say how much dissolved oxygen is actually needed by these aerobic biological organisms, and how much is actually missing from that water. So with biochemical oxygen demand, it's essentially saying how much dissolved oxygen is needed. So on to moving on. This basically is going to be a good way to test to see how clean the water actually is. Because if there isn't much dissolved oxygen in the water, if there's a high demand for oxygen, that means the water's probably pretty polluted. There are bacteria, there are viruses that are pulling that dissolved oxygen out of the water. So this is going to be a measure essentially of organic compounds that are actually in the water. So it's a good way to test. Problem is it takes a long time to do it. So with slide 13, when we look at biochemical oxygen demand, if you look at a pristine river, you're going to be looking at about 1 milligram per liter of water, which is pretty good in regard to cleanliness of the water. It's pristine, right? So it's going to be super clean. There aren't going to be any pollutants in it. There aren't going to be a lot of bacteria that are drawing the dissolved oxygen. So moderately polluted rivers are going to have about between 2 and 8 milligrams per liter. Municipal treated sewage is going to be at about 20 milligrams per liter. That's why they say don't drink the water from the purple pipes. Untreated sewage is going to be 600 milligrams per liter. So again, the takeaway from this is essentially that the higher the biochemical oxygen demand, the higher the level of pollution. Because what it's saying is we need this oxygen. There isn't enough oxygen, dissolved oxygen in the water because it's being utilized by these pollution sources, these viruses, these bacteria, things that are drawing the dissolved oxygen out of the water. So slide 14, chemical oxygen demand, is essentially going to be the exact same thing. So the higher the chemical oxygen demand, the higher the pollution is going to be. So the nice part about chemical oxygen demand is this is a test that's very readily used over biochemical oxygen demand by water treatment plants because it's much faster to do. It's quicker to perform. So they tend to utilize the chemical oxygen demand in water treatment districts to find out how clean the water actually is. So that's why this is a very valuable test. They use this much more readily in water treatment plants. On to slide 15, water quality surveillance. So we'll talk a little bit about water quality surveillance, and then I will probably pause and start another video so that way you can break it up into 2 videos. Water quality surveillance. So the EPA, the Environmental Protection Agency, is very busy with water quality surveillance. They do the best they can. I mean, they have so many other tasks ahead of them that they do the very best they can with regard to water quality surveillance. So throughout the country, we have 1,000 fixed stations nationwide. So yeah, I mean, just think about this alone. Minnesota has 10,000 lakes, okay? So obviously there aren't too many places that, in Minnesota alone are being tested by the EPA. And then in addition to that, the USGS, the U.S. Geological Survey, also has about another 500 fixed stations. And they're looking at dissolved oxygen, biochemical oxygen demand, chemical oxygen demand, pH of the water, how much suspended solids, and among that, a number of other chemicals as well, like lead and mercury, cadmium, phosphorus. So they're monitoring these things all the time. But again, it's really tough, with 1,500 total fixed sites between the EPA and U.S. Geological Survey. There's a lot of water that's not getting tested. So certainly you cannot rely on the EPA and the USGS to make sure that the water you're drinking in a national park is actually clean. So that's why you take a water pump with you that's going to filter the water. On to slide 16. The Clean Water Act of 1977 made some specific requirements. One of those being that toxic priority pollutants were going to start being analyzed much more readily. This included pesticides and metals and other lethal carcinogenic, mutagenic, and teratogenic toxins. So you remember carcinogens cause cancer, mutagens cause mutations, teratogens cause birth defects. Okay, so they started looking at these things and saying, we really need to make some priorities in regard to the toxics that we're actually looking at in the water. And then we started looking at conventional pollutants like suspended solids and acids and grease, the biochemical oxygen demand, and things like that. Excuse me. And then non-conventional pollutants like nitrogen and oxygen, aluminum, chlorine, ammonia, things like that. So they started looking at these different levels that are actually in the water themselves, so that they were essentially considered non-conventional sources of pollution. And then we also started looking at something called the NPDES, which is the National Pollution Discharge Elimination System, which people basically discharging pollutant into waterways from any source have to apply and obtain a permit. So it doesn't say you can't dump pollutants in the water. It says you just have to have a permit to do it. So NPDES states that you have to be able to obtain a permit to dump any number of things into a waterway, and this can include pollutants and toxicants and things like that. I work in vector control. I have to have an NPDES permit to put pesticides in waterways. Okay, so I'm gonna take a break right here, and then I'm going to come back with the second video. So this would be basically your video for Tuesday, and then the follow-up video, which will probably be about the same length and time, will be the video for Thursday. So again, I encourage you to just watch them both. That way you can absorb and enjoy the information and not have to worry about it for the rest of the week. Okay, so I'll be right back.